if those two guys are close to each other, those two guys doesn't have to be that close to each other, but they have to be at least a certain proximity. So that's the general intuition. They can be far away from each other, but somehow it is bounded by this parameter delta. This formal definition might be difficult, yeah? You might find it difficult, but you don't have to understand it very precisely. You have, yeah?
Sorry, why did you start with the if from the image? So if the images are close, then the pre-image, the x and y also have to be close? And not the way around, like if x and y are close, then their images.
No.
No?
No, you have to, yeah, precisely, you have to have it in an opposite direction. And why like that? I would say that simply because it works, yeah? Because the whole definition of topology, which I will give you in a moment, is based on the reversed image of F somehow. So what is interesting for you is if you look at the image of a function, you are interested from where it came. That's what's interesting, yeah? So, for example, if you look at this operation here, and you look at the final, result of all these operations, you are interested from where this image came. That's the crucial topological question. So, so that's the one definition. I will reformulate this definition later because, as you see, this maybe this is not obvious. This thing here, yeah, it means distance, yeah, it means distance, and this thing here also means distance, yeah? in a real space, so it means that this notation means distance between f(x), fy, and here the distance between x and y.
Maybe this confusion was because you put the quantifier inside, and maybe it should be before distance between f and x minus f.
You mean this one?
Yes.
This thing, yeah. Maybe we can put it here as well.
And the implication should be from like it is now. So for such that you should put an implication just. Maybe this would be better understandable.
The implication is that if those guys are close,
yes,
then those guys are close. Yeah, that's the implication. Okay. Now, what I wanted to say is, also I would like to introduce another notation, which is that we'll use the following notation. It's D, that's R, and it's A, and it means all elements B from the space such that the distance between A and B is less than R, less or equal to R. Yeah. Which means it is a disk. It is a disk of radius R around A. Okay. That's the typical notation in topology. Because why you understand it like that? I write this C here. Yeah. Why you understand like that? Because you have all the elements from the space which are at the distance from A not greater than R. Okay? That's the notation. That's the distance. So if you imagine all the points from the space which are at a distance not greater than r from the point A, then it's exactly a disk. So you have A here, and you think of all the points which are not farther away from A than R. Then it's exactly a disk. It's for two-dimensional disk. It looks like that. Is it clear?
Are there infinitely dimensional disks?
Yeah, of course. Yeah. You can imagine also a disk which is in an infinitely dimensional real space, for example.
It is R omega.
Yeah, you can imagine. You can write omega. Yeah, you can write omega if you want. It's a cardinal number. I don't want to go into details here, but you can imagine that your space has infinitely many dimensions, and your disk measures the distances. Your disk is based on measuring the distances on all of the axes, real axes. Yeah. And finally, you can also have, you call it like S. Like
then the space has to be somehow bounded, yes? Am I right? There has to be this R somehow measured. Because one thing is if there are many dimensions, the other one is if it's, I know how to say, ograniczone, boundable, and unboundable. So if it's unboundable, how can it be measured?
You can measure the distance on every axis separately. Because if you want to say something about the distance in the n-dimensional space, it's infinitely dimensional space, it's something different. Because it's difficult to measure distances in an infinitely dimensional space. But here, what you can say, what you want to do is you just want to define an infinitely dimensional disk. So you make it in a simple way. You say that it has a distance 1, for example, on every axis. And that's it, nothing more. You don't measure distances in general here. Okay, and a sphere, it's a sphere. It's pretty much the same. Everything is the same. Instead of the fact that you put equality here, equality rather than inequality. Yeah? So a sphere, it's the same situation, but you look only at this boundary here. Yeah? And there is nothing inside. Yeah? So a disk is when it's full inside, that's a disk, and a sphere is when it's empty. And what is important is that this sphere has a dimension 1. Okay? Because disk is two-dimensional, but sphere is one-dimensional, because it's only the edge, only the boundary. Okay? Is it clear? Yeah. Intuitively. Nope. Yes? Okay. Now, we need, we need more definitions, unfortunately, because we need a broader vocabulary. So another definition is the definition of a neighborhood. So, let's say, definition. A neighborhood of a point A in n-dimensional space is any set n, let's say, which contains disk around A. Yeah. Non-trivial disk. Non-trivial. Trivial disk is a point, yeah, where the distance is 0. Then it's trivial. Non-trivial. So, for example, just to draw a picture, you have a point A, and you have a kind of a set N. And if there is a ball, a disk around A here, let's say, that is contained in N for some delta, for some radius, then it's a neighborhood. Yeah? So every time you have a set into which you can put the point A with some disk around, then it's a neighborhood. So for example, if you have a point here, point B, then the question is N a neighborhood of B or not? No? Why not?
Because part of this disk is outside.
Yeah. So, independently on which type of disk you would draw around this point, you will go outside of N. So it means N is not a neighborhood.
If there is any.
Excuse me?
If there is any outside.
Yeah, if there is any outside, yeah, that's true.
The disk needs to fit into the N.
Yes, yeah, this needs to fit into the N. So it's in a space X. Alright, so now, okay.
So if you have the B point on the closemost point of the N line,
Yeah.
it could be in the neighborhood of A, because you could draw a disk that goes just to this border. And
Yeah,
then
if
you cross it.
it's close to the border, it's fine, because you will find a tiny disk.
But
around.
it could be on the border,
Yeah.
in the closest point possible to A.
There is no such point in a continuous space, at least.
But A doesn't matter here, because N is a neighborhood of A. N is a neighborhood of A. But we are speaking now about B, yeah? And for B, it doesn't matter where is A, actually, yeah? So
N is the neighborhood of A, or the disk around A is the neighborhood?
N.
The N is.
The N is neighborhood, yeah? So a neighborhood of A, a point A, space is not near. Is any set N which contains a disk around A. Yeah? So this N is neighborhood. Yeah? So you have A, you have a disk around A, and then it means N is a neighborhood. And you have, if A was here, as B is, then it wouldn't be a neighborhood. And as well, also if A would be here, it wouldn't be N. Then N wouldn't be a neighborhood of A, right? A has to be inside of N, in other words. Right, and now maybe the definition of topology. Definition. I already said something about it before when I was talking about these intuitions, but let me put it in a formal way. So, T is topology if it is maybe I'll put symbols here. If T is contained in the power set of X, right? Okay? No, I told you already what is a power set. So T is a subfamily of a power set. It might be full power set, but it doesn't have to be full power set. And it fulfills the following such that the following conditions are fulfilled. So the empty set is in T, okay? And the whole space is in T. That's one thing. Secondly, yeah, that will be difficult, but if you have a family I will explain it in a moment, okay? Such that okay, yeah, that's difficult. Let me explain that. So, because it's written in a very general setting, but I will try to make it easier in a very simplified situation. What are these U's? Okay, so you have like a number of sets. Let's imagine 4 sets. U1, maybe 5 sets. U2, U3, U4, U5. Okay? And all those sets belong to T. Okay? So U1, U2, U3, U4, U5 belong to T. So this thing here is the family of sets. It's the description of the family of sets. You have U indexed with lambda, yeah? And this lambda belongs to a given set of parameters, it doesn't matter. You have a set of sets, right? Such that every element from this set is in this T. Then the sum of these sets, the sum of all those sets, is an element of T. So, which means that if you sum everything, so it means consider everything together, yeah? That's sum. If you sum everything, then it also belongs to T. Do you understand that? Because it's a crucial moment, I would say. So a topology is such a family that if you have given family of elements of this topology, then the sum of those elements is also an element of T. So whenever elements belong to T, then the sum of the elements also belongs to T. Okay? And there is also a third condition. If U and V belong to T, then the common part of U and V also belongs to T. Okay? Which can be illustrated like this. If you have U and V from T, then the common part, this is common. This symbol here signifies the common part of it. Also belongs to T. Okay, so that's the definition of topology. And I guess that will be the last notion before the end of this part. So we have like 10 minutes more or 8 minutes more to discuss it. So please, as it's the most important word that we'll learn today, please be sure that you understand what is here. We can try to discuss it on an example if you want. So, do you have any questions regarding this? Let's try to use an example, okay? Maybe here. Let's get back to our set X, which consists out of a shoe and number 5. Okay. Can someone say what could be a topology here? Because there are a few topologies that can be defined on this set. But just give an example of a topology here.
Power set.
The power set, very well. So the topology would be the following. The empty set, a shoe, right? 5, and a shoe and 5. Yeah? That's one example. And why it is a topology? Why it is a topology? Because it's a subset of the power set, right? So this condition is fulfilled. Empty set is there, the whole space is there, because it's here, right? Then, if you have a sum of objects here, then if you have a number of objects here, then the sum of those objects is also here. So what type of sums you can have here? For example, you can have empty set and a shoe. So if you add those two guys, you will have a shoe, because empty set is empty, and the shoe is here. Or you can, for example, have a shoe and 5. Okay? If you add those two guys, you will get a set consisting of a shoe and 5, and it's here, because it's here, right? Or you can have a bigger sum, like for example, empty set and 5 and shoe and 5, for example. Like 3 elements. You have those 3 elements, and you add them together. And the sum is already there, because the sum of those 3 elements is a shoe and 5, and it's here, right? Now to check, the last condition, if you have 2 sets, then you want to check if the common part of those 2 sets is here. So, for example, you have a set consisting of 5, which is here in this topology, and you have a set consisting of 5 and a shoe. Right? What is the common part of those 2? The common part of those 2 is 5. And 5 is here. So this condition is also fulfilled, right? So it was a very good example. Now, but there are others.
Empty set and X.
Empty set and X. Very well. So let's consider it. Maybe we will put it in blue, okay? So that was first example. And now second example. You say empty set and the whole space X, right? Very good example. Why? Because, oops, let's check it. It is contained in the power set, right? Because empty set and X these are subsets of X. Empty set and X are elements of this. So this condition is fulfilled, right? Now, if you have a sum of elements from here, then we ask if you have a number of elements from here, we ask if the sum is included here. So what can be a sum of elements here? You can have, for example, an empty set and X. If you add an empty set and X, you will get an X. And X is already here. And basically there are no other sums here. You can also add empty set to empty set, which is empty set, or X to X, which is X still, because a set and a set is still the set. And also you can check this condition, and you ask yourself, if you have 2 elements from this topology, does the common part of those 2 elements is in this topology. So what is the common part of empty set and X? It's the empty set. So it's already there. Okay? Is it clear? Very well. Okay. But you can also name another topology here.
Maybe 1, 2, and 3. No, with this example.
Yeah, this here. Yet another example of a topology here.
If we take just the empty set, the full set, and then one of the two. Sorry, empty set, shoe, and shoe and 5.
Okay, so we try empty set, shoe, and 5. Okay, so let's check if that's a topology, okay? So it is contained in the power set, so that's right. It contains empty set, it contains the whole space, which is a shoe and a 5, right? Then we ask if it contains sums, okay? So what we can add here? We can add the empty set and the shoe, and we'll get a shoe, and the shoe is here. We can add empty set and shoe and a 5, and it's shoe and a 5, and it's here. We can add shoe and the shoe and a 5, and it's shoe and a 5, and it's here, right? So all these possible sums that you can imagine are already here. Yeah? All the sums of all possible elements are already here. And also you can try to check the common parts. So let's think, what is the common part of an empty set and a shoe? It's the empty set, so it's already here. What's the common part of an empty set and shoe and a 5? It's the empty set, so it's already here. What's the common part of a shoe and a 5? It's the shoe, so it's already here. And there are no other possibilities, okay? So that's also a topology. And what is the last example possible?
The shoe exchange for 5.
Yeah, exactly. So we can do the same trick, but instead of a shoe, we put 5. Very well. And we won't check that because it goes in a symmetrical way. It's the same situation, right? So as you see, in this situation, when you have a set with two elements, all elements of its power set form topologies. So you have a two element set, and you have 4 topologies which can be defined on this set. Which is not the case in case of bigger sets. Yeah? So if you have a set with 3 elements, then there are some subsets of its power set which are not topologies. Yeah? But we are out of time now, so we can try to check it later after the break.